Welcome back. In this lecture, we'll discuss a local search method known as greedy descent. So earlier we introduced greedy descent. You're picking a random assignment of variables initially, and then you are now selecting the variable that participates in the most number of conflicts and changing its value. We also looked at an alternative to this that we were able to pick any variable at random, and we didn't have it necessarily be the one to participate in the most number of conflicts. So what if we did this? What if we had a combination of both and we just say, hey, 70% of the time we're going to pick the best variable, otherwise we're going to pick the variable, or 70% of the time we're going to pick the best variable, otherwise pick any variable that is in conflict. And that is because a mix of these two has been shown to work better than either alone. So this opens up a whole class of algorithms called stochastic local search. And we've already talked about greedy descent. Random walk, here we're just picking the variables at random, so we're randomly walking through the search space. And we have this other idea called random restart, which we decide we're going to reassign values to all the variables now. And maybe we do this 1% of the time or something like that. And some of these might be more complex than others. And the thing is often it's been the case, as we mentioned earlier, that a probabilistic mix might work better. So here are some variants of greedy descent. Select a variable and to change and a new value for it. So most improving step is find the variable value pair that minimizes the number of conflicts. So we have so we look at all variable value pairs, and we're going to pick the one that, hey, if we change this, the total number of conflicts goes down. So next is a two-stage choice. Select a variable that participates in the most conflicts, which is our traditional greedy descent we talked about so far. But then we're going to select a value, instead of doing it random, we're going to select a value that minimizes the number of conflicts. We can also look at this in terms of any conflict. So select a variable that appears in any conflict, and we can do that at random. Then we can just go on to selecting any variable at random, because it may be the case that variables that are not in conflict are driving many of the other variables to be in conflict. So for example, if you remember in the CSP lectures, we looked at, we had like E has to be less than D, but if E is, say, a very high number, like 3, the other values for the other variable are much more restricted as what you can put in there. So maybe just selecting a variable at random, or at least doing that every once in a while, may help. And so the other thing is selecting a variable and value at random, and just accept the change if it doesn't increase the number of conflicts. So what steps are involved? One is to measure the number of conflicts for a given assignment. We may even want to weight the conflicts, some as being higher than others, especially for dealing with soft conflicts. And so, in this, moving from hard constraints to soft constraints is often what's referred to as relaxation. So if we want to move from not permitting any conflicts to maybe just considering the weight of those conflicts, we might now have an easier problem to solve. And so if A is a total assignment, we can define H of A to be a measure of the difficulty of solving a problem from A. And this is essentially looking at developing a heuristic function in much the same way we did with A star. So that concludes our discussion on greedy descent. Please stay tuned for more content.